sir. Reading you loud and clear.
I send you.
Project Mercury was born October 7th, 1958. Program approval was granted 1 week after the establishment of the new National Aeronautics and Space Agency. Program mission: put a man into space, orbit him around the Earth, and recover him safely. Program requirements: select a suitable launch vehicle, build a spacecraft, and train men to fly the space mission. Atlas, vehicle selected to insert the spacecraft into orbit, a 1.5-stage liquid propellant launch vehicle with 5 engines, 2 booster engines, a sustainer engine, and 2 small vernier engines. The total thrust produced by the Atlas vehicle, 360,000 pounds. The airframe skin, made from thin stainless steel, makes up the fuel and oxidizer tanks. 160,000 pounds of liquid oxygen and 73,000 pounds of kerosene-type fuel burn to provide thrust for 5 minutes of powered flight. Originally designed as an intercontinental ballistic missile, the Atlas needed structural modification to carry the Mercury spacecraft. Also, an adapter for the upper conical section. This work was undertaken together with a vigorous program of static testing. Also being tested was the Redstone rocket. This launch vehicle, developing 76,000 pounds of thrust, was selected to boost the spacecraft into a suborbital ballistic flight path and thus qualify all systems for later orbital flights. Like the Atlas, the Redstone vehicle was modified for manned application. A system was devised for both launch vehicles, which would automatically sense an incipient failure or critical condition and shut down the engine immediately. From the onset, pilot safety was the prime factor in Project Mercury.
The Little Joe airframe, produced especially for Project Mercury by the North American Aviation Corporation, houses 4 large Castor solid fuel rockets and 4 smaller recruit rockets. The holes in the base of the vehicle indicate the relative sizes of these rockets. The Little Joe booster is unguided and derives its aerodynamic stability from 4 large tail fins. One of these fins is shown here as it is being assembled on a special fixture. Preliminary testing of the completed airframe is accomplished in a static test tower at the North American Company plant. The use of the Little Joe boosters in the Mercury development program provides an economical means for simulating many of the most severe launch, emergency escape, and recovery conditions. Final assembly of the booster takes place at Wallops Island. First, the rockets are erected, then the airframe is fitted around them. The capsules used in the early phases of the Little Joe program are manufactured in NASA shops and do not contain many of the systems and subsystems that will be part of the Mercury operational capsules. The escape tower and rocket, however, are final production hardware, being qualified in the Little Joe test program. Before the firing, the scaffolding is removed and the booster is supported on a simple launcher. A flight test program using full-scale models of the Mercury capsule was initiated. These boilerplate models duplicate fully both the weight and the external shape of the final Mercury operational capsules. Their construction is greatly simplified through the use of heavy welded sheet metal. They do not include many of the Mercury subsystems, such as the life support system or the communications equipment. These boilerplate capsules have been used to develop the parachute system, to validate recovery procedures, to check the functioning of the escape system, and to determine the motions and heating of the capsule during re-entry. Large cargo airplanes were used in the development of the parachute system. Full-scale boilerplate capsules were dropped from Air Force C-130 aircraft at high altitudes. The capsule slides out of the plane's cargo door on a sled. As soon as it is clear of the aircraft, the sled is released. and after a period of free fall, the lid on the antenna canister is released. Then the small drogue parachute is ejected by a mortar charge. This parachute reduces the capsule's swinging motions in the early stages of the descent. At a predetermined altitude, the small parachute pulls the top antenna housing away from the capsule and automatically deploys the main descent parachute. The capsule then descends toward the water. The main descent parachute is a 63-foot ring sail type cargo parachute. Upon impact on the water, the parachute is released from the capsule by a small explosive charge to avoid dragging the capsule in the wind. The airplane drop tests also provide an opportunity to exercise the various recovery devices and to further develop and improve recovery operational procedures. After impact, a smoke generator is energized to emit smoke from the tops of the capsules to aid the visual search. This is a view of the capsule from an approaching recovery vessel. A green dye marker solution is released from the base of the capsule to help make it visible from greater distances and altitudes. And a small antenna on top of the capsule transmits signals from the automatic rescue beacons to searching ships and aircraft. Concurrent with the airplane drop test, an extensive rocket flight test program has been initiated. At the National Aeronautics and Space Administration's launch site at Wallops Island, Virginia, tests were performed to develop the emergency escape system and qualify it for future use on manned flights. Escape from the launching pad can be simulated by lifting the capsule from the ground with the escape rocket as the only means of propulsion. After ignition, the escape rocket burns for only 1 second. It appears to burn much longer here in this slow motion sequence. In an in-flight abort, the capsule would be carried at least 250 feet away from its booster. The capsule and the tower then coast together to the peak of the trajectory. The gentle rotation is caused by a deliberate offset of the rocket thrust to provide a lateral displacement of the capsule as it leaves the booster. This rotation would impose only small loads on the pilot inside the capsule. At the maximum altitude, the tower is separated from the capsule with a small rocket. Then the antenna housing lid is released. And the small drogue parachute is ejected by the mortar charge. After the swinging motions of the capsule have been reduced, the drogue parachute and the antenna housing are jettisoned, automatically deploying the main descent parachute. On impact, the parachute is automatically disengaged from the capsule. In an off-the-pad abort, the capsule reaches an altitude of more than 2,000 feet. The main parachute was deployed and opened fully above 1,000 feet, providing ample time for the use of the reserve safety parachute if required. In these tests, the capsules were recovered by helicopters and returned to Wallops Island for further use in the test program. The tests also provided an opportunity to conduct development work on the recovery and pickup techniques. The Atlas booster was used in the most severe test of the Mercury system that has been performed to date. In that test, a research and development version of the capsule was launched from Cape Canaveral, Florida. The combination of the developmental Mercury capsule with the Atlas booster was nicknamed Big Joe. The trajectory for this flight was shaped to simulate a return from orbit without actually going into a satellite orbit. The objectives of the Big Joe test were to check the capsule's heat protection at nearly orbital speed, to verify its aerodynamic stability, to provide a severe test of the onboard recovery system, and to develop recovery procedures in a realistic test situation. The Big Joe capsule was taken to the launching pad several days prior to the shot. Within the capsule is special instrumentation to measure the loads, noise, motions, and temperatures during flight, and a control system to orient it into the proper attitude after its separation from the booster. As the capsule is hoisted to the top of the gantry, the plastic heat shield designed to dissipate the tremendous heat of re-entry is clearly visible. The capsule is mated to the top of the Atlas booster and attached with a special clamp. The clamp will be released explosively after the Atlas engines are shut down. The special Mercury capsule used in this test was not fitted with an emergency escape system. The booster and capsule systems and their instrumentation were checked and rechecked during the days prior to launch. The Joint Defense Department Recovery Task Force was deployed along the capsule's intended flight path. The launch was made in the early morning hours so that a full day would be available for recovery operations if required. In the blockhouse, the countdown proceeds for many hours before the firing. Here, the function and readiness of thousands of component parts of both the booster and the capsule are recorded. The malfunction of any one of these parts could make the difference between a successful flight and a complete failure. Minutes before the firing, liquid oxygen is piped into the booster, which is now ready for flight. As the countdown approaches 0, the final switch is closed and Big Joe is launched. This Atlas booster carried the capsule to an altitude of 100 miles and to nearly orbital speed. The Big Joe capsule was then separated under conditions that closely simulated orbital re-entry. On the recovery ships, the capsule appeared as a flaming fireball as it streaked back into the atmosphere. Many hundreds of miles from Cape Canaveral, airplanes vectored to the impact area and soon picked up the capsule's recovery signals. 2 destroyers raced to the area and sighted the capsule about 8 hours after launch. The capsule was picked up by the destroyer Strong and returned for a detailed inspection and for an analysis of recorded data. It had survived its re-entry in excellent condition. The recovered Big Joe capsule represents a major milestone in Project Mercury in that it positively demonstrated the validity of the Mercury design concept. In the fall of 1959, 3 Little Joe vehicles were launched successfully. The first was a test of the basic booster system. In the second test, the escape mechanism was activated intentionally during the early phases of flight. This test simulated a severe escape condition that could occur in an orbital flight launch. The capsule was recovered undamaged shortly after landing. On takeoff, 2 of the casters and 4 recruits are ignited, giving a thrust of 250,000 pounds. The smaller recruits burn for only 1 second, while the casters have a burning time of 27 seconds. The second pair of casters will be ignited just before burnout of the first pair, but at an altitude too high to be visible from the ground. The remarkable stability of the Little Joe booster is well demonstrated in this flight. Later on in the flight, the escape rocket is ignited, separating the capsule from the booster. At the completion of the escape sequence, the capsule falls back toward the ocean and parachutes are deployed. Recovery is accomplished by Navy ships. After recovery, the capsule is hoisted on board with a special net-like device and returned to NASA facilities for visual inspection and for an analysis of the data recorded during the flight. The third flight was used to perform an escape maneuver at high altitude. After a planned escape, the capsule coasted to an altitude of 55 miles and was recovered 200 miles from the launch site. On this flight, a small monkey was within capsule and was recovered alive and well at the end of the flight.
January 21st, 1960. In a test of the emergency abort system under maximum airload conditions, Little Joe number 4 also carried a rhesus monkey. The flight lasted 8.5 minutes with a successful landing 10 miles offshore. No man-conceived project can guarantee 100% reliability. Yet, Project Mercury must come as close as is humanly possible. Since Project Mercury is a manned flight, the pilot must have an escape capability during the powered portion of his flight. This emergency escape system gives him that capability. The craft was picked up 4.5 minutes later by one of the Recovery Force helicopters. The research and development flight test provide continuing training for the recovery forces in addition to verifying design concepts. Only 16 months after contract initiation, the first flight test of a production spacecraft involving an off-the-pad abort was entirely successful. After launch, the spacecraft escape tower combination makes a stable climb to more than 2,000 feet. At the peak of the flight, the escape tower separates, falling well clear of the spacecraft. The drogue chute slows and stabilizes the craft, maintains the proper attitude for main chute deployment. The antenna canister is jettisoned, automatically deploying the main chute. The main parachute is intentionally reefed for a few seconds to reduce the opening shock, then opens to its full area. A 63-foot main chute brings the craft to an approximate 20-mile-an-hour landing, the impact cushion taking up the initial shock. The main chute is released to avoid dragging the craft, and the emergency chute is jettisoned. Within minutes after landing, a helicopter from the Mercury Recovery Forces picked up the spacecraft.
Minus 5 seconds, mark. 5 seconds and holding momentarily. I have a commit arm light. T-minus 5 seconds and counting, mark.
On July 29, 1960, the first Atlas-boosted flight of a production Mercury spacecraft was attempted. This research and development effort ended after 60 seconds of flight with an unexplained breakup of the vehicle. Manned orbital flight will require more research and many more flights. In November 1960, the first Redstone-boosted Mercury spacecraft was scheduled for launch. The Redstone launch vehicle qualifies the actual hardware, the production spacecraft, the actual systems in space. The vehicle will not place a spacecraft in orbit. It will boost the craft through a ballistic trajectory for recovery on the Atlantic test range.
This first launch attempt comprised a strange admixture of failure and success. Slow motion photography recorded a sequence of events which followed the start of MR1's engine. As the Redstone lifted from the pad, the two tail plugs supplying ground electrical power failed to pull loose in the correct sequence. A resulting undesired voltage potential was sensed by the vehicle's abort sensing system, which told the engine to shut down. The Redstone then settled back onto the pad. Noting the shutdown, the spacecraft's electronic brain signaled for escape tower jettison. Sensing further that it was at a low altitude, the spacecraft then initiated deployment of its parachute landing system. Mercury Redstone number 1, a flight test failure, a successful demonstration of its system's capabilities. Less than a month after the first attempt, the same spacecraft was launched by vehicle MR-1A into a suborbital ballistic flight. All events occurred as programmed. The spacecraft attained a velocity of 4,909 miles per hour, was weightless for 5 minutes, and sustained deceleration of 11 Gs on re-entry. Recovery of the spacecraft after a total flight time of 15 minutes and 45 seconds was accomplished smoothly.
On the MR2 flight, Ham is a stand-in for the astronaut. The van that brings him to the launch pad is the same van that the astronaut will use. Ham's form-fitting couch is like the one the astronaut will use. The first United States astronaut will take the same ride, in the same van, out to the same launch pad, and up the same elevator to the top of the rocket and into the Mercury spacecraft, just as Ham is doing today. MR2 nears launch time. In the control room, quiet efficiency is the only outward sign. The flight director presides over the countdown. 4, 3, 2, 1, 0. Fire, liftoff. And Ham is on his way. In the control center, the flight surgeon's eyes are glued to his console, monitoring Ham's condition. Concern mounts. Ham's heartbeat and respiration climb fast. MR2 now leaves a visible trail, and it is flying faster and higher than it should. An abort condition is indicated. Something is wrong. But with the abort system operative, the Mercury craft begins to behave exactly as programmed. The Mercury craft landed farther downrange than programmed. The abort system worked, but Ham sustained 18 G instead of the normal 11 that was expected. But Ham is fine, and MR2 was successful. Test objectives were achieved. Mercury systems worked in space. A man could have made the trip into space and back safely. MR2 was a significant milestone on the highway to man's flight into space.
On the next Mercury Atlas flight, static firing gave notice of launch readiness.
Three successful unmanned flights had proved that the Redstone launch vehicle and spacecraft were ready for manned application.
After delivery to the Cape Canaveral launch facility, spacecraft number 8 was unwrapped and underwent rigid systems checks and testing in Hangar S, from which it was moved to the launch site and raised for mating with the Atlas launch vehicle. The payload, a simulated astronaut, was scheduled to pass in one orbit around the Earth, and upon recovery and data evaluation, to have been the forerunner to a manned orbital mission. The escape tower is attached to the spacecraft.
-6.
In the blockhouse, the first half of the countdown went smoothly. Telemetry equipment was checked and readied. Data recorded here was used for further evaluation of the Atlas launch vehicle. The spacecraft was thoroughly inspected, and no structural damage was incurred, either from the high dynamic loads of the abort or the impact, and is presently being refurbished for another flight test. A maximum dynamic load test of the escape tower sequence at high altitude was planned for April 19, 1961. The modified spacecraft was mated with the Little Joe launch vehicle. During the launch, a hang fire developed in one of the Castor rocket motors. The resultant down-pitching of the test vehicle booster produced a much lower trajectory than was planned. The abort took place at 13,000 feet, at Mach 1.47. No structural damage had been experienced, either in the abort or in the landing. All test objectives are considered to have been met and exceeded.